masses small m and capital M are initially at rest at an infinite distance. Right, at an infinite distance, mass small m and capital M are rest. That means initial velocity of small m. Let's say the velocity of small m is v(I). Velocity of this one, right? V capital M I, initial velocity. These two are zero. These two masses are kept in infinite distance. That means gravitational potential is also zero because you know the formula. Gravitational potential energy minus G capital M small m or R square. If the distance is infinity, that is also zero. Right. Due to the gravitational attraction, they reach at a distance d. These masses are reaching at a distance d due to the gravitational force of attraction. Hence, obtain a velocity is velocity. Let's say the velocity of mass small m is Vm final. Velocity of mass capital M, V capital M final. Okay, this is mass small m. This is mass small m. This is capital. Okay, right. What we can say. Next, what is their relative velocity at this time? At this time, their relative velocity. Before finding the relative velocity by conservation of momentum, by conservation of momentum, we can say, right, the momentum of this mass is equal to momentum of this. That means small m into, I am writing the magnitude of it, V small m x equal to capital M into V capital M x, right? Now we can find the ratio. That means V small m final over V capital M final. That will be capital M over small m. Okay. What is the relative velocity? Well, let's say the relative velocity be relative. Relative velocity in the sense these two are moving together. So we have to say if we find the relative velocity of small m with respect to capital M, we have to change the direction. Then that will be the sum. V M final plus V capital M final. Right? That will be this velocity. Right. Now we can express this relative velocity in terms of their mass. What is this? If this is capital, if this one is capital M, then this will be small m. The ratio is capital M also. So what will happen? If you want to find small m, shall we write like this? Okay. V small m f. That means the final velocity of mass small m over V relative velocity equal to ratio small m is, right? We can compare with this. Relative velocity, that summation. So for the total mass capital M plus small m, right? These small m is correspond to capital M mass. So we can say capital. That means in the numerator capital M, denominator m plus m. Right? The ratio will be like this. Similarly, right? Similarly, we can guess that other relative velocity, other ratio also, right? Now I'm going to erase this. We can also find the velocity of the final velocity of the mass capital. That will be velocity of capital MS over velocity of relative velocity is equal to, right, m plus m over, this is correspond to smaller, right? This is correspond to smaller, right? Okay, now we can use conservation of mechanical energy. That means total mechanical energy is conserved. Total mechanical energy is conserved by conservation of mechanical energy, right? Kinetic energy initially, plus potential energy initial equal to kinetic energy final plus potential energy final. There are two masses. Those two masses are initially kept at infinite distance and the initial velocity is zero. So initial kinetic energy is zero. Initial potential energy is also zero because these two masses are kept at infinite distance. We know the potential energy is equal to minus B capital M small m over. What is the formula for potential energy? G capital M small m over D. Right, potential energy. We already have, right? G capital M small m over D. Right? Since D is infinity, for the initial case, D is infinity. So initial potential energy is zero. That's the reason this is zero. Okay. So this will be final kinetic energy of mass small m is half into small m into V small m final whole square plus potential energy. Potential energy is kinetic energy of small m is like this. Kinetic energy of capital M is half into capital M into V ns whole square minus potential energy between these two minus G capital M small m over D. Because when these two masses are reached at a distance speed, the potential energy will be like this. G capital M small m over D is equal to half small m. Vm squared in the sense. What is Vm squared? Vm in the sense V smaller. That means capital M over n plus n whole square into V rated whole square according to the formula we have obtained earlier. Plus this one half capital M. Right, this is capital M. This is capital M plus small m. Right, small m over capital M plus small m whole square. V rated whole square. That's it. Because this one we have no here. Now we can cut capital M small m. Small m capital M is there, right, in both sides. Right now, if we solve this, we can get the answer. Right? For this, no any shortcut like this, right? If we solve this, we can get the answer. Uh, in left side and right side, capital M small m is common. So if we cut that, G over D is equal to this is half, right? Small m is cut, capital M whole square. That means one m will be cut. So m over n plus m whole square dot V relative square plus half into this capital M and this one is cut. Small m is also cut. One small m will be there. Small m over capital M plus small m whole square dot V relative. So from this we have to find V relative. What is that? That will be if you solve this. If you solve this, this will be V over D. Right. This will be G over D. So G over D in the left side, that will be half into 1 over capital M plus small m whole square is common for here and here. So, and we relate to whole square is also, we can take it out. Right. Now, what is inside the bracket? Capital M, this capital M is there and small. So, capital M plus small m over capital M plus small m whole square. So, this will be half into V relative whole square over M plus M. So, from this V relative equal to 2G into capital M plus small m over D, right? This will be hidden square. So the option is the first one.